All of you, please give your attendance in the chat box. I repeat, those who have joined the class may give their attendance in the chat box. Let me present my screen first. Can anyone please respond whether my slides are visible or not?
Yes, sir, visible.
Okay, thank you. Yes. So if you remember in the last class, we discussed few small things related to fatigue failure, such as notch sensitivity, fatigue stress concentration factor, notch sensitivity factor, relationship between fatigue stress concentration factor, stress concentration factor, and notch sensitivity, how this relation affects when there is no notch and when there is a notch, how the relation affects. All these things we have seen. We have also seen the difference between the endurance limit of a particular component as well as the endurance limit that we get from the rotating beam fatigue testing machine. That is, this is the difference. Normally the endurance limit of any mechanical component is somewhat less than the endurance limit of the component that we test in fatigue testing machine by some factors, that is Ka, Kb, Kc, Kd, and these factors are called derating factors. So if you remember in the last class we have discussed till this topic. If anyone can answer. If any one of you can answer that, I think what I remember is till the last class we have discussed till this topic. Hello.
Yes, sir.
Okay. So now we need to first evaluate the value of Ka, Kb, Kc, Kd, and then we will multiply it with Se dash to get the value of Se. And what is Se dash? This also we have seen in the last class, that if it is a steel, Se dash will be zero point 0.5 times of SUT. If the material of a component is made up of cast iron, Se dash will be zero point 0.4 times of SUT. Do not need, you cannot, you no need to remember all these values. This will be given in the data book. Fine. So let us find out what are these Ka, Kb, Kc, Kd, and how we can find out these derating factors. What is Ka? Ka is your surface finish factor. This surface finish factor, it the relation it is found out by some experimental relationships developed by the scientists called Shigley and Mishki. For steel components, for steel components, the surface finish factor is given by Ka is equal to A into SUT to the power B. What is A and B? A and B are the coefficients that are given in surface finish table. You can surface finish any component by these four ways. That is by ground method, by machined or cold drawn method, by hot rolled method, and by forged method. If the surface condition is ground, the value of A is 1.58 and value of B is minus 0.085. If the surface finish condition is machined or cold drawn, value of A is 4.51, value of B is minus 0.265. SUT will be given in the problem either in direct manner or in indirect manner. But by looking the problem, you have to see which surface finish condition has been used. According to that condition, you have to substitute the value of A and B, and then you use this expression to get the value of the first derating factor, that is surface finish factor. Again, no need to remember these values. It is given in the design data book. If you see the design data book which I have given in the Google Classroom, these data are there. Any doubt so far?
No, sir.
Okay. Now, if say after putting all these values, that means after putting the value of A, after substituting the value of SUT and B, if this KA value, if it is coming to be greater than 1, then you have to take KA equal to 1 by default. Say the KA is coming out to be 1.45, 2.51, 3.64. You have to take it always equal to 1. It is only applicable for steel components. It is, remember, if the component is made of steel, normally we use either steel or cast iron components in order to design any component that is failing by fatigue. But if the component is made up of cast iron, then the Ka value is always equal to 1. No need to use this expression, no need to go for these values. These values and this expression is only applicable for steel components. For steel components, for cast iron components, always Ka is equal to 1. Always Ka is equal to 1. And for steel component, if after substitution of A, B and SUT, if this Ka value is coming out to be greater than 1, then you have to take Ka equal to 1. So this is your surface finish factor. Any doubt in this surface finish factor?
No, sir.
Okay. Next is KB. What is KB? KB is the size factor, because it is not necessary that every time in the industry you are using a 10 diameter shaft, 20 diameter shaft. Many different sizes of shafts are available. How size factor affects in fatigue loading, that is given in this slide. Normally, shaft is subjected to bending and torsion. We know that shaft can twist, shaft can bend. So for bending and torsion, this surface factor, that is the size factor KB is given as follows. When the diameter is less than or equal to 7.5 mm, then you have to take KB equal to 1. When the diameter lies between 7.5 mm to 50 mm, you have to take KB equal to 0.85. And when the diameter D is greater than 50 mm, you have to take KB equal to 0.75. But these values are applicable only when the component, that is shaft or any member, is subjected to bending and torsion. Is it clear? Hello.
Yes, sir.
Fine. Okay. Now there are two more empirical equations which you can use to find out the value of KB. If the diameter of the shaft, if the diameter of the shaft is less than 51 mm, and if it is lying in between 2.79 mm to 51 mm, fine, then the empirical equation which is to be used to find out the value of kb is kb equal to 1.24 times of d to the power minus 0.107. But remember, you have to use this equation to find out the value of kb only when it is written in the problem that use empirical equation. If it is not written, then you can check this chart and accordingly you can substitute the value of KB. Now see, in this chart, if you see clearly, if the dia is greater than 50 mm, you have to take KB equal to 0.75. But say if the dia is 100 mm, 150 mm, 200 mm, then how to take the value of KB? In that case, you will use the second empirical equation, that is when dia of the shaft lies between 51 mm and 254 mm, then the value of KB is given to be 0.859 minus 0.000873 times of D. And what is D? D is the diameter of the shaft. What is D over here? D is the diameter of the shaft. But if the shaft is subjected to axial loading, see, all these data and this empirical relation is valid when the component is subjected to bending and torsion. But if the component is subjected to axial loading, that means either you are pulling it or you are pushing it or you are compressing it, then the value of KB is taken to be 1. Again, no need to memorize it. All these data are given in that design data book. Is it clear to all of you how to calculate the value of size factor KB? Any doubt?
No, sir.
Okay. Next is KC. What is KC? KC is known as reliability factor. Normally, if we design any component for fatigue, reliability plays an important role. How reliable is my product is in fatigue, because fatigue failure takes some time to fail. It may take 1 day, it may take 10 days, it may take 50 days time. So during that time period, definitely reliability factor becomes the important role in designing. So on the basis of different reliability percentage, different values of KCs are available in the chart. If the reliability of any particular component is 50%, then you have to take KC1. If the reliability of any component is 90%, value of reliability factor Kc will be 0.897. If the reliability is 99.99%, the value of reliability factor Kc is 0.702, which is again given in the design data book. But while solving the or while designing the problem of fatigue, you have to see clearly in the question how much is the reliability factor given to you. According to that reliability factor, you have to find out the value of Kc. Is it clear? Any doubt so far? Hello.
Yes, sir,
No,
no
sir.
doubt.
Okay, so this is your reliability factor Kc, and the last factor, that is Kd, it is known as modifying factor to account for stress concentration. If you remember, I have told you in the last class that Kd is nothing but it is reciprocal of fatigue stress concentration factor. That is Kd is 1 by Kf. So in order to find out the value of Kd, first you need to calculate the value of Kf. Kf, how you will calculate? You know, in the last class I have told you that Kf is given by the relation Kf is equal to 1 plus Q times of Kt minus 1, where Kt is stress concentration factor. This also you know how to find it out from design data book. What is Q? Q is notch sensitivity factor. It will be given to you in the problem. Then you use this expression, get the value of Kf. Once Kf is known to you, take the reciprocal, you will get the value of Kt. So these are the four different derating factors which you have to take in account every time whenever you are designing a component for fatigue, because whenever you are designing a component for fatigue during that condition, you will be evaluating the real time endurance limit, and the real time endurance limit based on these values, that is Ka, Kb, Kc, Kd into Se dash. So is it clear how to calculate all these values? Surface finish factor, size factor, reliability factor, and modifying factor. Any doubt so far?
No, sir.
No, sir.
Okay. Now, two there may be two situations in the problem. Situation is when you are designing any component, for fatigue subjected to maximum shear stress theory of failure, then what is the value of endurance limit? Then we have already derived that in maximum shear stress theory of failure, fine, yield strength is what? Yield strength is that is SSY, that is yield strength in shear, is zero point 0.5 times of SYT. We have already derived in shear stress theory of failure. Similarly, when we are designing any component for fatigue, and that too when we are using maximum shear stress theory of failure, then SSE is what? SSE is endurance strength in shear, which is equal to zero point 0.5 times of SE. And what is SE? The SE is nothing but what we have calculated just now, Ka into Kb into Kc into Se dash. Is it clear? This is endurance limit in shear. This is the endurance limit value, whose value is nothing but AC dash is equal to Ka, Kb, Kc, Kd, Ac. Any doubt so far?
No, sir.
No, sir.
Okay. Secondly, the same component can be designed for fatigue by distortion energy theory of failure also. And if you remember, when we were discussing the distortion energy theory of failure, we have derived one relation. If you remember, a long derivation was there. Some 15 to 20 equations were there, and from that long derivation we concluded that the yield strength in, that is shear, that is SSY, is how much? It is 0.577 times of SYT when we use distortion energy theory of failure. Similarly, when I am designing any component for fatigue by keeping in mind distortion energy theory of failure, then this SSY becomes what? This SSY becomes SSE, that is endurance limit in shear, that is equal to 0.577 times of what? Yield strength we call about, but here there is no yield strength, there is ultimate, that is endurance limit strength, that is SE. So these 2 points you have to keep in mind. You have to see the question that whether the problem is to be designed for fatigue failure by using shear stress theory of failure or by using distortion energy theory of failure. Then accordingly you have to use this particular equation to get the value of SSE for shear stress theory and SSE for distortion energy theory of failure. Any doubt so far?
No,
No,
sir.
sir.
Okay. Okay, let us move forward. Fine. So this was the case. This was the case when shear stress is acting in any component and you are interested in calculating the endurance limit in shear. But there may be a case that only axial load is acting in any component, and it has been told to you that get the value of endurance limit stress for axial loading. In that case, again, this is an empirical formula. It will be given to you in the problem. Fine. Sorry, in the data book. This is given in the data book. That is when any axial load is acting in any component, and from that axial load, and if that axial load is variable in nature with respect to time, that means it is failing by fatigue. In that case, SE axial, that is endurance limit, axial endurance limit. Axial endurance limit is nothing but equal to zero point 0.8 times of SE. That is endurance limit, actual endurance limit of the component. And how to calculate this SE? We know that AC is equal to Ka, Kb, Kc, Kd, Ac dash. So by those concepts, first we will find out the value of AC, then we will multiply AC with zero point 0.8 to get the axial endurance limit when any component is failing due to axial load in fatigue. Is it okay? Any
Yes,
doubts
sir.
so far? Okay. Fine. So this was the overall concept of how we will design any particular component if in that component either bending, shear or axial variable load is acting. Fine. So generally there are two type of problems which we deal in fatigue. The first type of problem is when the component is subjected to completely reversed stress. When the component is subjected to completely reversed stress. And secondly, when the component is subjected to fluctuating stresses. Secondly, the component is subjected to fluctuating stresses. Fine. These two problems can be solved by two methods. First method is either you can design these problems for infinite life, or you can design these components for finite life. For example, if any component is failing in fatigue, if any component is failing in fatigue by criteria number 1, and if it is taking say 100 years to fail, then definitely 100 year is what? 100 year is nothing but an infinite life condition. Accordingly we will solve the problem. If any component is say failing by condition number 2, but for within 3 hours, within 4 hours, within 2 days, then that fall under the category of finite life. Then we will use the finite life criteria to design that problem. Is it clear to all of you? Any doubts so far?
No, sir.
Okay,
No,
other
sir.
people please respond whether it is clear or not.
Clear, sir.
Clear, sir.
Okay, fine. So presently we will design one component with infinite life. Then in the next class, I will show you how to design any component for finite life. Okay, fine. So let us take an equation. Let us take a problem. But before taking that problem, what are steps which you have to keep in mind? Who is joining now? I have to check who is joining. Riju is joining. Okay, so when we are designing any problem for infinite life, what are the steps that you should keep in mind? The very first step is endurance limit becomes the criteria of failure. That is true for the finite life problem also. Second step is the stress amplitude should be lower than the endurance limit stress. For example, if there is a ductile material and I know maximum limit of ductile material is what? Yield strength or yield point. So whenever I am designing any ductile material, as a designer, I should be keeping the strength of the material below the yield point. Similarly, as a designer, if I am designing any component for infinite life, I know that I know that that component is failing by fatigue. That means the maximum limit of that component is what? Endurance limit, endurance point. So while designing, whatever stress you are calculating, you should keep in mind that that stress value should be lesser than that of the endurance limit value within infinite number of cycles, so that it can withstand that infinite number of cycles, because the stress amplitude value, the calculated stress amplitude value, if it is more than the endurance limit value, then the design will fail. It will not sustain that infinite life condition. So you have to make sure that always the stress amplitude or the stress which you are calculating for your design procedure, it should be lesser than that of the endurance limit value. Is it clear? Any doubt?
No, sir.
Okay.
No, sir.
And how to get this stress amplitude value? This stress amplitude value, we can get it from the factor of safety equation. We know that factor of safety is what? Factor of safety is failure stress by allowable stress. So allowable stress is failure stress by factor of safety. Failure stress by factor of safety. So if the allowable stress is stress amplitude, and failure stress in this condition will be what? Will be the endurance limit stress, because we are designing a component for fatigue. So sigma becomes sigma A, and this failure stress is endurance limit AC by factor of safety. This is the equation. The same allowable stress can be a torsional shear stress also. Then that sigma becomes tau A. That is torsional amplitude stress. That is equal to failure stress. Failure stress will be what? Will be endurance limit stress in torsion. That is nothing but SSE. Just now we have seen in the previous slide, divided by factor of safety. Then this particular value, which value? This sigma A and this tau A, after the calculation part, you have to check it with the endurance limit value, whether it is more or it is less. If it is more, that means my design is failed. Again, I have to change some dimensions to get the correct design value. Is it okay? Any doubt so far?
No, sir.
No,
Not.
sir.
Okay, so now let us solve one problem related to this infinite fatigue life design. Okay, I think the time is 3:40. Okay, we will try to finish it within 20 minutes if we can do it. Let us read the problem. The problem is a plate made of steel 20C8 SUT is 440 Newton per millimeter square. 440 Newton per millimeter square in hot, rolled and normalized condition is shown in the figure below. So this is a steel plate. In this steel plate, at the central portion, a hole is being drilled of diameter 10 mm. Width of the plate is 50 mm, and the plate is subjected to reversed loading of 30 kilonewton, reversed loading of 30 kilonewton. Due to this reversed loading, the component is failing by fatigue. Okay, the notch sensitivity factor Q can be taken as 0.8. So the value of Q is given to us, that is 0.8, and the expected reliability of this component is 90%. Since reliability is 90%, we can easily find out the value of Kc from that table. The factor of safety is 2. A factor of safety is given to you. The size factor can be taken as 0.85. We know that size factor is nothing but kb. So directly the value of kb is given to you, that is 0.85. Determine the plate thickness. What is the thickness of the plate? That you need to determine for infinite life. That means due to this reversed loading condition, failure of this component in fatigue is uncertain. It can fail after 10 days, it can fail after 100 days, it can fail after 100 years. That means it is an infinite life problem. How we can solve it? Is the problem clear to all of you, or should I repeat it once again? Is it clear?
Yes, sir.
Other people, please
Yes, sir.
respond. Okay, fine. So the very first step is what? Calculation of endurance limit. I know that endurance limit AC is, this is actual endurance limit, and this AC dash is what? This is that endurance limit which we find out in laboratory by that fatigue testing machine, and we know the relation that AC is equal to Ka, Kb, Kc, Kd, Se dash. So first, let us find out Se dash. How we can find out the value of Se dash? We know, see, for that you check, it is written a plate made of steel. That means this component is made of steel. And if this component is made of steel, then from design data book, I know, from design data book, I know that for steel, AC dash is how much? AC dash is 0.5 times of SUT. So I will use this first expression to get the value of SE dash. Is it clear?
Yes, sir.
Yes, sir.
Fine. So SE dash is what? SE dash is 0.5 times of SUT. SUT, I think it is given in the problem. Yes, SUT is what? 440 Newton per mm square. So SE dash is 0.5 into 440, which is how much? Which is 220 Newton per mm square. That means this AC dash value is 220 Newton per mm square. But before this, you have to write this AC dash is equal to 0.5 times of SUT. How it came? You have to write in bracket that since in the problem the material of the component is steel, then from design data book page number so and so, you can check the page number right over here. Then from design data book page number say 5.5, since the material of the component is made of steel, so the equation of AC dash is 0.5 times of SUT. If you do not write these 2 3 lines, then you will lose marks, because how then you will justify that from where you have taken this AC dash is equal to 0.5 times of SUT? Because this AC dash will change from material to material. If the same problem is made up of aluminium alloy, then you have to use AC dash equal to zero point 0.4 times of SUT. You cannot justify it if you don't write the reason. Is it clear?
Yes, sir.
Yes, sir.
Hello. So always remember, not only this fatigue problem, whatever problem you are solving in design and whatever data you are taking from design data book, in bracket side you have to give the reason why you have taken that data from that particular page number, or else you will lose the marks. Fine. Okay. So this is your AC dash, that is 220 Newton per mm square. We got. Next is we have to find out the value of Ka, Kb, Kc, Kd. We know from the design data book that Ka is what? That is A into SUT to the power B. See, I have written over here from design data book, page number 5.31. The book which I have given to you in the Google Classroom, you check page number 5.31. This equation will be given to you. So you have to write it down, this line. So Ka is A into SUT to the power B. Now SUT I know that is how much? 440. I have to evaluate the value of A and B. How I can evaluate? For that, go back to the question. For that, go back to the question. It has been written in the question that a plate made of steel in hot, rolled, and normalized condition. From this line, that is hot, rolled, and normalized condition, can I find out the value of Ka? Hello, hello.
Yes, sir.
Yes, sir.
Fine. So this is what? This is the machining condition. So if I go back to my Ka, this is my Ka for hot rolled and machined condition. So which option will I choose? What is the value of A and B for my problem? Hot rolled and machined condition. What is the value
Sir,
of A and B?
57.7 and minus
Yes, yes,
0.718.
yes. Value of A is 57.7 and value of B is minus 0.718. So you have to write it down from design data book, page number so and so. Since the given problem is machined by a hot rolled process, so from design data book, page number so and so, I am taking A equal to this much, B equal to this much. Fine. So this is your A, this is your B. Just put it in that equation of Ka, get the value of Ka. Ka is coming out to be 0.72. Done. Next is I need to calculate the value of Kb. Kb is already given in the problem sheet is written. The size factor can be taken as 0.85. Size factor is nothing but Kb. So value of Kb is directly given to you 0.85. Next is Kc. What is Kc? I know Kc is reliability factor. So by reading this question, can I find out the value of Kc? By reading this question, can I find out the value of Kc? Hello.
So using which equation can we find the value of Kc?
You tell me, you read the problem. I'm telling me Kc is what? Kc is reliability factor. In order to find out the value of reliability factor, some hint is given in the problem. Tell me that hint. From that hint, I can find out the value of reliability factor.
Sir, expected
Can anyone tell
reliability
me
is
what is that hint?
90%.
So 90%
Yes,
expected
it is
reliability.
written. The expected reliability is 90%. That means when you will design this component for fatigue, reliability of this component will be 90%. So if I go back to my design data book and if I check my reliability factor, this is 90% reliability corresponding to 90% reliability. My Kc value is how much? 0.897. So you have to write it down from design data book, page number so and so. Since the component which is designed, it has a reliability of 90%. So value of Kc is 0.897. Is it clear?
Yes, sir.
So I got the value of Kc. That is Kc is 0.897. It is given in design data book table 5.37. Okay. Next is Kd. What is Kd? Kd is modifying factor to account for stress concentration. And I know that Kd is what? It is the reciprocal of fatigue stress concentration factor. That is Kd is equal to 1 by Kf. And I also know what is the relationship of Kf. Kf is, that is fatigue stress concentration factor, is nothing but it is equal to 1 plus Q times of Kt minus 1. What is Q? Q is notch sensitivity factor. And if you see in the question, is the notch sensitivity factor given to you? Yes, it is given to you. See, read this line. Notch sensitivity factor Q is zero point 0.8. So Q is given to you 0 0.8, but KT is not given to you. KT you have to find out from the design data book using those graphs. If you remember when I was discussing the stress concentration concept, I have shown you how to you read those graphs. From those graphs, you have to first find out the value of Kt, and before finding out the value of Kt, you have to analyze the diagram, that this diagram suits which graph. Yes or no? Hello. Hello.
Yes, sir.
Fine. So if you see, this is what? This is a rectangular plate with a central hole. This is a rectangular plate with a central hole. So if I go back to my those design data book graphs for stress concentration, let us go back. Yes, this is the graph which I will select from design data book. Yes or no? Wait. Yes, this left side graph I will select. Yes or no? Hello.
Yes, sir.
This left side graph I will select because this is a rectangular plate with a central hole. Diameter of hole is A, and for this problem, how I can find the value of Kt? If I see in x-axis, it is A by W. A means dia of the hole divided by width of the plate. So corresponding to A by W value, if I move upward, then the line where it will touch this graph, that particular point along y-axis will be my Kt. So let us find out firstly this A by W value in my problem. A by W value in my problem. So yes. So can you tell me what is A and what is W in this problem? What is A and what is W in this problem? A is the dia of the hole, that is 10 mm. W is the width of the plate, that is 50. So A by W becomes 10 by 50. A by W becomes 10 by 50. 10 by 50, which is 0.2. So corresponding to A by W equal to 0.2. If I go vertically, let us go. A by W is 0.2. Yes. A by W value is 0.2. This is my A by W value 0.2. So if I go upward, vertically upward, it is touching this graph at this particular point. From this point, if I go along negative x direction, I have to stop at this particular point, and I know this y-axis represent kt. So what is the value of my kt? What is the value of kt? What is the value of kt? It is 2.5. Yes or no?
Yes, sir. 2.5.
Hello. It is 2.5. So I got the value of kt to be 2.5. Yes, see, yes, kt is 2.5. So I got the value of kt. I can use this expression and I can get the value of kf. So kf will be equal to 1 plus q. Q is a zero point 0.8. Q is zero point 0.8 in bracket kt minus 1. That is 2.5 minus 1. So you will get the value of kf, that is fatigue stress concentration factor, to be 2.2. Now, what is KD? KD is just the reciprocal of KF, that is 1 by KF. So 1 by 2.2, and KD is coming out to be 0.45. Now, if you see, we have calculated all the four derating factors. Now we can calculate the actual endurance limit of the component. That is, AC is equal to KA, KB, KC, KD, SE dash. KA we have calculated 0.72, KB given in the problem 0.85, KC from the chart we found out that it is 0.897, and KD just now we have calculated, that is 0.45 into SE dash. SE dash also we have calculated, that is 0.5 times of SUT, that is 200. So if you solve this expression, you will get the value of SE, that is actual endurance limit for the specimen, that is nothing but 54.347436 Newton per mm square. Is it clear? Any doubt so far?
No, sir. Sir.
Okay, other people please respond whether it is clear or not.
Yes, sir.
Yes, sir, clear.
Okay, fine. So we have calculated the value of SE. But this problem is a bending problem or a torsional problem or an axial loading problem. Please tell me. In this problem, what is happening? Whether it is an axial loading problem, whether it is a bending problem, or it is a shear stress problem.
Action.
Yes, if you see in the diagram, both the ends of the plate, axial variable load is applied. Fine. And just now we have seen that for axial loading, AC axial is how much? AC axial is 0.8 times of SE. For axial loading, SE axial is how much? That is 0.8 times of SE. Just now we have read. So SE axial is 0.8 into this SE. So SE axial becomes, that is 43.477 Newton per mm square. That is endurance limit for axial loading condition. Is it clear? This SE axial. Any doubt?
No, sir.
Okay, so we have calculated the value of AC axial. I know that how I will design. That is, lastly, you have to find out what? You have to find out the amplitude stress. So for the problem, amplitude stress will be what? Sigma A equal to SE axial by factor of safety. Sigma A is what? AC axial by factor of safety. AC axial we have calculated 43.477 divided by factor of safety is 2. So permissible amplitude stress is how much? It is 21.73 Newton per millimeter square. That means maximum permissible endurance limit stress in axial condition for this problem is how much? 21.73 Newton per millimeter square. Now this permissible stress value should be lesser than the amplitude stress value for this particular component subjected to stress concentration, and we know that for a rectangular plate with a central hole, we know that KT is how much? KT is sigma max by sigma nominal. This sigma nominal for this condition, that is a rectangular plate with a central hole, is how much? Load P divided by W, that is width of the plate, minus this dia of the hole, that is D, this is area, into how much? Thickness of the plate. This is the equation. So the sigma A, that is the permissible sigma A of the problem, is how much? 21.73. Either this 21.73 value should be lesser than or should be equal to this sigma A value due to stress concentration. So let us equate it. That is, first let us find out that particular stress value. That is P divided by W minus A into H. The P is what? P is 30 kilonewton. P is 30 kilonewton divided by W. W is 50 minus A or D, that is dia of the hole, that is 50 minus 10 into thickness T or H, that I need to find out. That is T. So sigma A is 30 into 10 to the power 3 by 50 minus 10, that is 40 into T. Now this particular amplitude stress value due to stress concentration should be either less or equal to the amplitude stress value due to fatigue. So just equate these two equations, that is this equation equal to 21.73. Now if you solve it, you will get the value of thickness of the plate, and that thickness is how much? It is 34.51 mm, so near about equal to 35 mm. So in order to fail this component by fatigue for infinite life, thickness of this component should be equal to 35 mm. And this is what it has been asked in this problem. That is, find the value of the thickness. Is it okay? Any doubt in this problem? So this is how we can design any problem when it is subjected to fatigue failure for infinite life condition. In the next class, I will show you that how we solve a problem when it is failing by fatigue for finite life condition. That means if the component is failing within 10 hours or after 1000 cycles, after 4000 cycles, then how to design that component. So with this, then what I will do is I will end up the lecture over here, but before ending up, I will tell you the syllabus for my part. For my part, syllabus will be till the next class, because today I have solved one finite life problem. In the next class, that is on Thursday, I will make you solve one infinite life problem. So till that portion will be my syllabus for midterm 1. Okay.
Okay, sir.
Okay, sir.
So, okay, fine. So, if anybody is left